panel hosted by Unilumin. We're here today to discuss the challenges and advancements of direct view LED displays. Firstly, we're going to focus on the technology. We have more content to come that's covering manufacturing and applications. First of all, please allow me to introduce our guests today. First off, we have Nedi Nadoshari, who's Chief Scientist at Unilumin, and Steve Scorse, who's joining us, who is CEO at Unilumin UK. First off, Steve, if we can stick with you, what's the current development status of the latest LED display technology?
Well, the LED industry is now almost 30 years old. I mean, it's actually 1994, the first blue LED was invented, and that started off the LED industry we know it today, and it's gone through many iterations. Back in those days, it uses what was called DIP technology, which some people call through-hole, an individual light of red, green and blue, one individual. It wasn't until the early 2000s that the SMD technology we use today was discovered or productized. So that enabled higher resolutions, and SMD, by the way, is surface mounted device. So that was when we took those individual red, green and blue dyes and packaged them on a small micro PCB board to create an RGB chip. That enabled higher pixel pitches, or wider pixel pitches, and entered into new areas for applications such as meeting rooms and other things like that. That was further enhanced back in around about 2013 when what's called NPP or narrow pixel pitch versions of those SMDs came, and that then allowed resolutions to be increased to pixel pitches down to 1 millimeter or less. So LED went from, in that 20-year period or so, LED went from an initial technology that was in sports stadiums and billboards to this technology we see today, which is in meeting rooms, boardrooms, control rooms, production studios, TV studios, and all of those things. What's happened recently is that pixel pitch has got smaller and smaller and has driven some other developments. One of the challenges of the existing technology was robustness. As the pixel pitches become smaller, they become more fragile, and you have to be very careful that you don't bang them. You don't, have a briefcase knocks into a wall and damages it. They're not waterproof, so they're difficult to clean. And that led to the sort of development of a new technology to try to address those things, and that was called IMD. If you don't know what IMD is, basically it stands for Integrated Matrix Device. Really, a lot of people call it 4-in-1. So to improve the robustness of the solution, you take 4 RGB chips, and you make them into a single 12-chip product. 4 reds, 4 greens, 4 blues. Makes it a bigger package, means that it's more resistant to bumps and knocks. So it solves the robustness issue. So that's IMD technology, and that's been out a few years now. It hasn't dominated the industry. It hasn't really gone very far. It's used, but it's not taken over from SMD.
Did it work?
Well, it did to a degree. It did what was, what they say, it did what was on the tin. It solved the robustness problem, but calibration was less efficient, less accurate than SMD, because you were taking an average value for the reds, the average for greens, the average for blues. So there were some more artifacts than there is in SMD. So you won the robustness battle, but in terms of image quality, it wasn't quite as good as the SMDs that are used. So it hasn't taken over. What's happened then is that we've got a new technology which is really addressing those things, which is called COB. And again, COB, I say it's a new technology. It's a new LED technology for displays, but it's been in the lighting industry for 10 years. But in the lighting industry, COB, by the way, stands for chip on board. It started off as a solution to get the cost down on existing SMD displays, but by avoiding the needing to mount them on a single PCB, but to mount them directly on the board. But it was using the same what's called wire bonded SMDs as is used in the other technology, and it didn't really address all of the issues. It's had some challenges. Didn't have any better contrast than SMD, so it didn't improve the better image quality. It improved some things, but the latest versions of COB use what's called full flip chip. Flip chip is a much more stable technology than wire bonded SMDs. So using full flip chip COB technology, we've been able to both improve the display performance, so you've got higher contrast, you've got higher brightness, you've got more efficiency, also with a very robust solution. I mean, you've got the ability to hit these things, you can wash them, they're waterproof, they're dust proof, and they're very, very reliable. So this is the next generation, or the new generation of LED is moving now to COB and derivatives of COB using this full flip chip. And that's what we're here to talk about today.
So Steve, could you tell us about mini LED and micro LED, what they are, what are their uses?
Well, the terminology mini and micro are a little bit misused today. There's a lot of things that are really mini LED, which people are calling micro LED, but they're not true micro LED yet. So let's concentrate on mini LED, which is the main technology. Effectively, it's the latest derivative of COB, and it's focusing on pixel pitches down to around 0.8, 0.7 mil pixel pitch, up to about 1.8 mil pixel pitch, and in those areas, it's extremely a high performance product, very high contrast, very good uniformity, very stable, very long life. Because of the efficiency of these products, you no longer have the heat you had traditionally with an LED. I mean, you've probably touched an LED screen and felt that it was warm. With the latest mini LED solutions, its ambient temperature is about 37 degrees with a full image on full brightness. So that efficiency and temperature is a key feature to the long life now as well. There's a few other interesting features that mini LED has. One is it has a very uniform, soft image, which means it doesn't have the light spots you have with an SMD screen. So it has no moire. So in a TV studio, you don't have those interactive moire patterns with the CCD on the camera. So very, very useful for broadcasting applications. Micro LED is really the next generation. It's really for pixel pitches of 0.7 and below. And there's a lot of developments in micro LED. It's not just the chip. It's also the drive solutions, and there's a lot of new things there. And Neddy will go into that in more detail. But true micro LED is the next generation.
Fantastic. And Neddy, if we could turn to you, what are the technologies that will be consequential to the short-term and the long-term future of the direct view display industry?
So our industry is actually going through a stretch of accelerated, progressive, advanced technologies. This isn't normal because we are not necessarily known to be a high-tech industry. And the technology vectors that are relevant to us is way beyond just the LED technology or how the LEDs are packaged and so forth. It's a wide range of things that we in our industry are working on towards performing better and developing quality products and so forth. And it's important to actually talk about those things in advance of talking about the stuff that most people relate to, which is the LED technology. So, and maybe a brief mention of those things is not a bad idea. These range in the area of system design, in terms of control, and in terms of precision in mechanical design, precision in mechanical fabrication, as well as the LED itself. The LED itself is actually very relevant to our technology as it really relates to not only how we package it, but how we address the future needs of the NPP or narrow pitch products and so forth. So a brief mention of these other vectors of technology is important, but it's not what people are actually interested to hear about. If there is an interest, of course, we can talk about it separately and so forth. But as it relates to how we develop LEDs and how we address the future needs of the NPP, we can actually talk about the LED packaging and LED development itself. As it relates to LED, for example, I can tell you that there are a lot of new innovations in the fabrications of the LED. And it is not just the fabrication of the RGB dyes, but sometimes sort of a completely new way of thinking about how you develop R, G, and B, and so forth. So one of the things that deserves a mention is the unification of these wafer developments. So today, of course, the green and blue are developed on gallium nitride, and the red is actually developed in a different process. And some of these two are actually combined in the process we call color conversions and so forth. But there is a methodology and also a sort of a field of advancement in terms of how you unify these wafer developments. So not to separately develop green, blue, and red, but to maybe develop all of them at the same time using the same process. Some of the ones that are important to mention are activities in relationship to development of what's called a stacking. And a stacking means basically you're developing layers of color R, G, and B, and you can actually, through the methodologies using driving, how you drive those, you can actually decide which color or which waveform you actually induce. And this has been done actually right now in the form of 100 by 100 micron, which is sort of in the range of micro LEDs. But it will soon be reaching 4 micron dimensions and so forth, which would be very useful in our future. The other that is relevant to mention is a completely different methodology using a junction design. LEDs are junctions, right? So a particular LED junction design where you can actually change the physics of the junction by driving methodology and actually induce different color waveforms and so forth. So once again, it goes back to unification of the junction design. In other words, the advantage, of course, is that you only have one junction as opposed to 3 different junctions or 3 different LEDs and so forth. These are important to mention, but there are also advancements in the technology relating to LED that reaches out for low current efficiency, which is very important for us, as well as the drive towards actually more efficient emission, if you like. And so those are important to mention. But coming back to the packaging, our packaging technology is also going through many new changes. In sort of a follow-up to what Steve already mentioned, we've way past the lateral or wire bond COBs and then flip chip COBs and so forth. Now we are building products based on what's called a micro-in package, which is a micro device that is packaged essentially, not exactly an SMD, but similar to SMD, but it is a sort of a transitionary step in the evolution of the technology we follow. The technologies that we actually would be relevant in this realm are packaging technology, not just the LED packaging, but just the packaging technology. One that is important for us is what's called the WLCSP, or wafer level chip scale technology, or chip scale packaging. Right. Essentially what that is the SMD is basically a package that has body, a molded plastic body essentially, and it's designed to guide the light which is emitted from the LEDs to the outside. In the case of a WLCSP, there is no body to the package, so the substrate, or wherever the actual dies reside, becomes the dimension of the package. Huge number of advantages besides the fact that the package is smaller. The other advantages are the fact that the light is emitted completely differently. There is no direction of the light, so the light is emitted in a funnel which is wider. Therefore, the intersect of the lights from different adjacent packages causes a very, very short distance to the surface of the display, which avoids the morays, for example, and additional advantages to this WLCSP. So, but then we need to go beyond that, because this is just the stuff that we'll be toying with in the next year or so. If we are discussing technologies that are relevant to us beyond that, let's say 3 years to 7 years and so forth, first we need to talk about the technologies relating to how we drive these LED dies. Today, predominantly, most of what we build is based on what's called a passive matrix technology, which is sort of a grid structure where it's a matrix of how we drive and how we sync the current in order to light up the LEDs and so forth. That is being replaced by what's called the active matrix, which is sort of a dedicated drive to each pixel. It's a simple explanation for what really is, but active matrix is the future for us, because it avoids many of the issues that are that show up as rudimentary artifacts on the screen that are related to the active matrix and the capacitive drives and so forth associated with driving all of those LEDs. So that is now combined with a micro technology. We talked about acronyms and how abusive they are. I'll introduce you to a new one, which is called micro on CMOS. So in the technologies that I'm actually working on or developing IPs for Unilumin is in the area of micro on CMOS. And what that is that we combine the micro devices, very, very small micro devices, on a substrate that is made out of CMOS. CMOS is obviously where we build all microchips and so forth on. Instead of putting them on PCBs or putting them on other substrates, laminate stuff, we actually put it on CMOS. And in the CMOS, basically, we build the active matrix. And all of that is packaged on the WLCSP, where the connection bumps are actually developed as part of the TSV technology, which is a through silicon vias. And so the bumps are actually at the bottom of this CMOS substrate, and CMOS substrate has the driving technology. And of course, the LEDs themselves are either mounted or mass transferred on top of the CMOS as phase one of this. And this is a technology internally we call either intelligent pixel or UPC, which stands for another acronym, Universal Pixel Chip. So that's just a phase one. Going forward, actually, by the way, I forgot to mention that the CMOS not only includes the drive mechanism for the LEDs, but it can also include a lot of other functions, such as sensors, such as touch sensing, whole IR sensors for on-camera tracking, a lot of other things that are the technologies that could be embedded when the substrate is not just PCB, which is not active logic, if it's a CMOS. So anyway, moving past this, we can actually talk about technologies beyond that, because as I said, this is just a phase one. In other phases, we would this is referred to as D2W, or the device to wafer technology. In the next step, we go to what's called the wafer to wafer technology, W2W. So the wafer to wafer technology basically says, okay, now that we have the CMOS active matrix CMOS device, or which is used as a substrate, then what we will have another wafer that has combined R, G, and B, and this time we don't move the LEDs one by one on top of the CMOS. We will just hybrid combine those two wafers together, and this is a process called hybrid bonding, which is technology beyond the conversation today, but basically, essentially what it does is combines or attaches the gallium arsenide versions of the RGB and the CMOS and bonds them together. And now we actually have a solution, and we can dice these things and package them if we want, or very large packages in what we call a UDC, or universal display, UDE, sorry, universal display elements, which can be as big as 1980 by 1920 by 1080 and so forth. So anyway, these are the technologies that are that we will see in the next 5 years. And I think going beyond that, there's also a push towards the unification of the wafer, which is actually called the unification of wafer unification process. And that is to combine the fabrication of the LEDs with the fabrication of the CMOS. So now they're not two wafers that are bonded together, they're just on one wafer. And that is a technology that awaits a couple of few challenges we have in terms of how we can actually build efficient gates, CMOS, typically CMOS, but in this case, those logic on top of the gallium arsenide, which is a process that is utilized for building the LEDs. So these are all things that are waiting for us. I wanted to go back and mention the active matrix on glass and the process of TFT, which is also another interim process. Of course, there are people that are building products like that, Samsung Wall and so forth. But there are limitations to that, and that's why I call it a transitionary technology. The limitations are that first of all, we get to that point because there's already a vast investment in LCD panel manufacturers building the same products. So it's a very sort of a natural transition for our products to be built using that technology. And what that is essentially building a different versions of these active matrix product, which is called thin film technology, or TFT. And those are built on glass substrate, and then the LEDs, RGB, are mass transferred on top of the glass and so forth. So the problem or the challenges are that the TFT is using either amorphous semiconductor, or even now the newest version of the technology, which is called LTPS, or low temperature polysilicon TFT. So those technologies, there is still a limitation on the efficiency of the mobility of the electron through the junctions, because these are not CMOS. These are actually technologies that are developed as an inkjet deposition for the glass, and for reasons that are again beyond the conversations today, the mobility of the electron is very, very low. And what that means is that the amount of current that we need to drive in order to induce brightness, high brightness, is very high. Either we make the TFT junctions very large in order to be able to drive it very high, the transistors have to be large, or if they are small for like a NPP process and so forth, then we can't really produce very high brightness solutions. So that's why I think current generation of products that are being built out of Korea, for example, are based on this technology, but they all know that that's not the future, and they all have to transition and so forth. So yeah, these are just some of the stuff that we are looking forward to working on, and many of these, of course, are things that we are creating an IP around in Unilumin and developing patents and so forth for.
Amazing, thank you. On that note, how will Unilumin be positioned to leverage proliferation of advanced technologies to lead to future evolution of direct view displays?
Okay, so not all direct view display companies are the same, right? Mm. So many of our colleagues agree that what differentiates the companies, the ones in Asia, for example, are their willingness to invest in future, and their willingness to actually invest in innovation. What differentiates these companies essentially is, you have a layered view of competency of a company in this field. For example, at the first layer, the companies that know how to build displays. Maybe above that is a layer that allows the company to actually mass produce for cost reasons, and many of the companies that we actually interact with or our competitors fall into that category. Above that, there's sort of a step that allows the company to be able to deliver quality and performance. And yet above that, there is the ability to build products that are quality, performance, but consistently. And that's not an easy thing to achieve. There's maybe one or two companies in our industry that actually do that. And then the very top of this is the ability to introduce your own IP or innovation into a product that is not available to other people and is valuable. And that is a rare thing in our industry. So what I have to say is that Unilumin is led by people that are willing to invest in future and are willing to actually pursue R with the capital R, not just R&D and so forth. And to that extent, there's a lot of effort that I lead in the company that focuses on technologies that are relevant not just immediately, but 5 to 7 years from now.
Fantastic. Sure. Thank you so much for all that valuable information. Here we're going to focus on the manufacturing and supply chain. We have more content available that covers the technologies and also the applications. To talk to us today is Steve Scores. Steve is CEO, Unilumin Group UK. Thanks for coming, Steve. What are the changes in dynamics in our industry supply chain as a result of chip-on-board technology?
Well, we first introduced chip-on-board technology solutions in the U-Mini series back in 2016. That was a whole new manufacturing process. Then it was called mass transfer printing. So we've been developing that process since then. We had the first mass production of that process in 2018. So over the past 5 years, we've been optimizing that, improving it, and there's a whole range of things that have been done to optimize that process in terms of interior materials control, innovations in the packaging technology, improving the advanced calibration for COB technology, which is different, optimizing color consistency. So we believe that we're now ahead of our peers with this technology, and it is no longer, I would say, in its infancy. It's now getting into some degree of maturity.
I believe that Unilumin has possibly the largest LED manufacturing base in the world. Could you tell us anything about it?
Unilumin's largest factory is 400,000 square meters in Shenzhen in China. In addition to being the largest factory in the world in LED, it's also the most highly automated. We spend a lot of money, a lot of time in optimizing the production process to improve standardization, robotizing as much as we can there. So this is considered to be a sort of a halo factory within the industry. It sort of has all of the advanced features. We've subsequently opened a dedicated production line for mini micro LED, which is chip on board technology within that factory. Again, that's state-of-the-art, highly automated.
And if we could talk about that process a little, but mostly about maintenance and repairs, we do hear say that LED chip on board modules cannot be repaired. Is that true?
Well, let's start in a different place. Let's start looking at what are the failure mechanisms of LED in general. And if you look at SMD, surface-mounted devices, and IMD, or the 4-in-1 type devices, the traditional LED products, the failure mechanisms you see in those can fall into three areas. Let's say the first is, I would say, we call it insufficient stability. In other words, they use a process called wire bonding, which is where there's a red, green, and blue wire bond, which could be gold, could be copper. Those connect each chip to the PCB. Delamination or lack of contact within that wire bond is one of the most common failures of an LED. That requires the LED to be removed and resoldered or replaced. That's probably the number one issue. Then you have what we would call low-level protection. In other words, humidity is one low-level protection. I mean, SMD devices are often not waterproof, so you don't have to just keep water away from them. You keep high humidity away from them because they can absorb it. They can be affected by static. They can be affected by dust and dirt buildup from fingers and things. So all of those things you don't have in COB because it's an encapsulated technology. So it's washable, it's cleanable, it's dustproof, it's anti-static. So it doesn't have those failures. And then you have physical damage. As the pixel pitch gets smaller and smaller, the likelihood of there being some physical damage, someone banging a briefcase into the wall, or and then knocking it with something, or even an engineer damaging a PCB when they put another one in a replacement. Often you can have an LED that's knocked off by the actual engineer that's replacing the one that was faulty. So you have to go back and replace another one then. So none of those things happen in COB because of the encapsulated technology, the fact that there is no wire bonding, it's a direct bonded flip chip. So because most of those things don't happen to COB, you don't have anywhere near the number of failures. So it's a very highly reliable technology. So what we call it full flip chip common cathode COB. That is the sort of the whole branding of it. So it has very high surface protection, waterproof, dustproof, static resistant, shockproof, bump resistant. Also, it is very efficient in terms of power efficiency. So that means that there's very little heat, so it runs much cooler. And as you probably know, the cooler you can keep the product, the longer the lifetime. So that's another key thing. And also it has something we call a cool screen technology, which means that the screen will never get more than about 37 degrees, even on full brightness, 37 degrees Celsius, that is, for the Americans. So that is much, much less than an SMD product. probably 10 or 11 degrees less, certainly at least 8 degrees less than an SMD with the same brightness level. So those all improve the reliability of the product. Now, to get to your question, can you repair it? In the field, you can't repair it. You can't go and repair that board in the field or even in a subsidiary office. You would then exchange it with the spare board, it's the set of spare boards that come in the spares kit with the product. But you can repair it on a dedicated production line, a dedicated repair maintenance production line. So we have such dedicated production lines for repair using automatic chip removal, automatic bonding, and that's all in the factory. So today, for repairing the boards that need repair, they would ship back to the Shenzhen factory. They would be run through that production line to remanufacture effectively there. So you end up with a line that we can do about 100 modules a week there. That's the turnaround time. I shouldn't say that's the capacity. That's the turnaround time. If someone sent 100 modules in, it would take about a 1 week, 7-day process to repair them on that production line. And then they ship out again as fully repaired, basically remanufactured product.
Thank you. That's interesting rundown of it. Can we talk a little about the costs that surround it? Are things like mini LED products, are they on the expensive side?
They were. When we first entered mass production with the U-Mini 0.9 back, say, 2018, it was premium priced. There was a significant premium for the COB U-Mini compared to the premium level U-Panel S, which was the high end of the SMD product line. That is no longer the case, and part of that is down to the fact that, as I said in the beginning there, it's the maturity of the production process. The yields are now higher. The supply chain is also more mature, so that is the costs in the supply chain have come down as well. So now you have a solution where you have in, say, the U-Mini Pro, which is the latest iteration, which is the third iteration, the third generation of U-Mini products. You've got the extreme high brightness, extreme contrast, very high efficiency, very high reliability, high robustness, great viewing angle, and you've got a product that is comparable or even lower cost than an SMD product of the same performance or similar performance and the same pixel pitch.
Absolutely fantastic. Thank you, Steve, for all that information. Very insightful, thank you. Here we're going to focus on the applications, and we have more content available that's covering Unilumin technologies and the manufacturing process. First of all, allow me to introduce our guest today, Nedi Nodar Shahi, who is Chief Scientist at Unilumin. Welcome. And Steve Scorse, who is CEO of Unilumin Group UK. And joining us on screen, we have Ted Romanowitz, who is Principal Analyst and Head of Pro Displays at Future Source Consulting. Steve, can we start with you? What are the key applications for mini and micro LED as of today?
Well, there are numerous applications for mini and micro LED. You have to look at effectively, it fits anywhere that an SMD wall fits effectively, but there are some areas where the specific advantages of mini and micro LED play a key role in making them a very, very nice fit. So you're looking at things like the high stability of the technology, the very high contrast compared to SMD technology, high brightness, high efficiency, in other words, low power usage, and a high display effect. So anything requiring one or more of these will be drawn into the mini micro LED area. So, as example, control rooms, conference rooms, broadcast, these are sort of key areas, but also government education, and as costs come down in particular, those areas become more of a target market. And then you've got other applications requiring where high protection is an issue. You know, as you get to the smaller pixel pitches, as we've discussed in some of the other presentations, smaller pixel pitches, sub 1 millimeter in particular, using SMD technology, are quite fragile devices, so they're susceptible to physical damage, or certainly not suitable for use with as say a touchscreen without having a glass overlay. While using mini micro LED technology, you can have direct touchscreen access without an overlay onto the screen surface, because you have the protection and you have static resistance, dust resistance, dirt resistance. They're waterproof, and they're very, very ideal for those sort of applications. And in the future, there's absolutely no reason why you can't have outdoor displays that are using COB technology. Today we don't have outdoor displays, but as we develop the high brightness versions, that's something that can happen as well. There's other things there that there's certain applications there where there's a very, very good sweet spot for COB and mini micro LED, and one of those is the virtual production market. And I think that's going to see a major development in the use of COB, mini LED, micro LED, as pixel pitch requirements get smaller and smaller.
Neddy, would you mind expanding on that for us a little bit? Maybe the prevailing technologies that will be important to the burgeoning industry of virtual production, or even extended reality and the on-camera market.
Yes, of course. Yeah, so this is a market that is moving in the direction of sort of new innovations and technologies that are required specifically. First of all, we need to fix some of the problems that we have, because many of the products that we offer in this market today, as the whole industry does, is mostly in the form of whatever products that exist now that may actually be okay for on camera, but that's different than actually building products that are specifically made and designed for on camera. The problems we need to fix are the obvious ones are the aliasing, which happens a lot, and there are flicker issues that are caused by a number of problems, not just refresh rate, by the way. Many people think it's just refresh rate. And there's content discontinuity issues, and also the synchronization that relates to that. So to the extent, and banding, of course, that is a result of aliasing. So the efforts to actually resolve some of these issues has led to a design of these products from scratch. In other words, rather than fixing problems, addressing the problems in advance, and actually building a particular architecture that is evolved around the requirements that are set by the camera. To this extent, you have to assume that this not only addresses the problems that I just mentioned, but also adds features, architectural features that are important. Some of those could be, for example, the much higher frame rate, obviously, but also particularly, especially as the on-camera screen's pitch gets beyond 200 ppi, which is about 0.12 millimeter eventually. You would have a dead space available on the screen to address the on-camera tracking, for example, with the sensors, or you could build in synchronization, communication mechanism for synchronization that is linked to the shutter rate of the cameras directly, because that's one of the traditional problems that we face. There's a video skew, a huge amount of video skew between the content as it gets actually rendered on the screen versus the shutter rate or the frame by which the camera actually sees that content. And that's, of course, very different from the way human brain and eye processes the image on the screen versus how the camera sees it. And so to this end, the synchronization is really, really important. And synchronization to where the content is actually emitted, not the input to the wall processor where the content is fed into the screen. So all of those actually, in addition to some of these new features, are going to be the things that we will see very soon in the products that are designed specifically for this market.
What would you say is the change in dynamics in our industry as a result of the advent and the dawn of new cutting edge technologies such as micro LED?
So the micro LED as it relates to virtual production, you mean, or in general? So in general, that's sort of a very vast topic in itself. I think the competency or the proficiency of the companies in our industry actually creates a huge change in the dynamics of how different companies react to the advent of these, the dawn of these new technologies. Specifically the micro LEDs, because you asked about the micro LED, is sort of a new thing that addresses many of the deficiencies that we actually live with and have lived with our existing architecture for many years. I would say maybe more than 25 years. So to this end, the micro LEDs almost require the push towards active matrix driving schemes. They require the advent of what's called the black to light ratio, which is is slightly different than a fill ratio, which is the ratio by which you actually have light emitting from the screen versus the surrounding, which is typically black. All of those things are actually technologies that are either addressed by companies immediately or they are basically ignored. So the dynamics of the change that affects our industry relates mostly to the competency of the companies that are willing or are prepared to actually invest in those technologies more than anything else.
Understood. Perhaps at this point we could bring in Ted to help us understand some data and analysis at this point. Ted, could you help us with what's the market share for LED technology compared with other technologies like LCD, projection and so on, and where is that expected to go over the next 5 years?
Great question. And the market is definitely in transitional growth. Thank goodness we've recovered from the global COVID pandemic. The market is increasing at a healthy compound annual growth rate. If you look at the snapshot on the right-hand side of the slide, it shows that the market jumps from 33 billion in 21 to almost 50 billion in 26. But look at how LED, its share will increase from 23% to 40%. LCD specifically drops from almost 60% to 50%. So a dramatic impact. And as we get towards the end of the century, the impact will be increasingly, more severe, where LED will become the leading display technology in the late 20s, early 30s, without a doubt.
Ted, what would you say is the growth in demand for narrow pixel pitch technology compared to others, and how is this impacting on the vertical markets?
Yeah, and if you look at the key performance indicators, LED across the board is growing at more than a 20% compound annual growth rate over the next 5 years, but dramatically the majority of the growth is in the narrow pixel pitch ranges. That's where you're seeing the dramatic jump, and it's for exactly the reasons that Nettie has talked about, right? These technology transitions from SMD to IMD, as well as to mini LED, and then eventually true micro LED. So though that technology transition evolution will drive the impact, will drive the transition to more and more narrow pixel pitches. And the really important thing, I think, is that transition will return us to a decrease in ASP erosion. So pricing, especially for ultra narrow pixel pitches below 1 millimeter, will start to come down and become increasingly cost effective, especially towards LCD flat panel displays. And if you look at it from a vertical perspective, the growth is amazing, right? What you'll see is, I'm going to kind of break this down into three different areas: digital signage, presentation, and then technical applications of LED. So if you look at digital signage itself, the standard and narrow pixel pitch shares are, very mature. We don't expect them to change very much. What we do expect is that ultra narrow pixel pitch will enable exciting new close-up viewing experiences, and this will really impact some very important market verticals. For example, retail, media, and advertising will LED will enable a higher impact image and expand the length of impression for the people that the retailers, the marketers are trying to influence. So that's very, very important because of the wider viewing angle, higher brightness, better colors. There's a plethora of reasons, as Steve mentioned. And then another great example is hospitality, leisure, stadiums, and venues. Right now, a lot of the use of LED is in higher pixel pitches, where it's in digital signage. The displays are located higher up, so your viewing distance is much further. So you can get away with using 2.5 or 2 millimeter type of pixel pitches and still have a retina type display. With ultra narrow pixel pitch LED, what that allows you to do is allow, viewing up to, sort of a meter away. So you'll see it in public spaces at eye level. This is a major, major shift. It'll unseat LCD technology in those spaces. And then on the presentation side, in corporate education as well as hospitality and leisure, ultra narrow pixel pitch will begin to be used in medium and large meeting spaces and classrooms, whereas a lot of the time now they're relegated to executive spaces or much larger, grander spaces. With the viewing distance being so close, they'll be able to address the user experiences in those smaller meeting spaces. And one of the stats that Future Source Consulting tracks is we do corporate end user surveys. There's over 70 million meeting rooms in the world that LED could address with this ultra narrow pixel pitch. That's a tremendous number. And then finally, on the more technical side, in control rooms and broadcast, we see that ultra narrow pixel pitch will support the shift towards smaller spaces. In the control rooms, you're seeing smaller, more geographically dispersed control rooms instead of a single large control room. So again, smaller spaces, tighter quarters. You need a more narrow pixel pitch to get the viewing experience that the client wants. And then with broadcast, as Nettie mentioned, the narrow pixel pitches enable a much better on-camera experience, and they also support smaller stages, which is a trend versus the larger grand stages. Fewer of those are being built versus the small and medium-sized stages. So, LED will give a lot of flexibility in set and stage design as we get to more narrow pixel pitches. So those are some of the major trends that have been happening, and the impact that we see moving forward with ultra narrow pixel pitch.
Fantastic. That's so insightful. Thank you so much. Thank you, Ted, Steve, Neddy. Really valuable information. Thank you so much. And thank you for watching.